In passive electronics, the standard rule of operation is simple. As you increase the voltage across a component, the current flowing through it rises proportionally. But to build precise timing and relaxation oscillator circuits, engineers needed a component that actively breaks this rule. They required a device that acts as a sudden electrical dump valve. This voltage current graph compares standard linear and diode curves against an unusual alternative. The downward dip represents a condition called negative resistance. Inside this specific zone, the rule flips entirely. Current violently surges even as the driving voltage collapses. Achieving this specific negative resistance profile is the essential mechanic for building the oscillators that dictate timing across complex hardware systems. During the early era of solid-state electronics, achieving that curve meant relying on a specific physical device, the unijunction transistor, or UJT. The UJT successfully delivered the necessary negative resistance, but the physical geometry required to make it work embedded a rigid, unchangeable limitation into every circuit it powered. By deconstructing the subatomic physics of the original UJT, we can isolate exactly where this fatal constraint lived and see how its successor, the programmable UJT, eventually bypassed it entirely. Understanding this evolution bridges the gap between raw, solid-state semiconductor physics and the flexible, highly controlled logic of modern IC design. Examining the transition from the UJT to the PUT illustrates a move from hardware defined by physical geometry to hardware defined by external circuit logic. To understand the limitation, we first have to look at the geometry of the raw materials. This block diagram shows the UJT's baseline structure, a continuous N-type silicon bar with contacts at both ends, labeled base 1 and base 2. The defining alteration is the emitter, a P-type region alloyed into the side, crucially offset closer to base 2. That asymmetrical PN junction is the sole mechanical source of the device's complex voltage-current curve. Here is the equivalent circuit schematic that engineers use to mathematically model that single piece of silicon. The PN junction acts as a simple diode, feeding into two internal resistors, RB1 and RB2. Together, these two resistors represent the interbase resistance, the baseline physical resistance of the unbroken N-type bar from top to bottom before any triggering event occurs. Because the P-type insertion point is physically off-center, it naturally splits the silicon bar into an internal voltage divider. This built-in divider sets up a highly specific triggering threshold within the semiconductor. Any external supply voltage applied across the two bases is immediately divided by those internal resistors. This animated schematic calculates the critical ratio of the lower resistor, RB1, against the total interbase resistance. This exact ratio is the intrinsic standoff ratio, denoted by the Greek letter eta, dictating a firm voltage threshold directly at the internal PN junction. For the device to fire, the external voltage applied to the emitter must exceed this internal ratio threshold, plus the standard forward bias drop of the diode itself. Looking at the handwritten notes at the bottom of the page, this exact breaking point is formally defined as the peak point voltage. As long as the emitter voltage stays even a fraction of a volt below this peak point, the entire device acts as an open switch, remaining entirely in a state of cutoff. This mathematical threshold is an electrical dam, holding back the circuit until the exact required pressure is achieved. When the rising emitter voltage finally crosses the peak point threshold, the behavior of the silicon radically changes. The forward bias junction opens like a floodgate, violently injecting a massive concentration of positive charge carriers straight down into the lower silicon matrix. This sudden influx of positive charge carriers floods the lower N-type bar, causing it to lose its high resistance state and become highly conductive. Looking at this characteristic curve, you can see the macroscopic result. The physical resistance of the RB1 region plummets from thousands of ohms down to tens of ohms almost instantly. This creates a snowballing regenerative effect. The sudden drop in resistance pulls more current into the device, which in turn injects even more holes, driving the resistance down even further. This specific physical phenomenon is called conductivity modulation. It is the true subatomic engine that drives the negative resistance curve. Once fully saturated, the device locks into the on state, dumping current until the emitter supply is externally choked off below a minimum holding value. The UJT effectively translates a microscopic flood of subatomic particles into a violently abrupt macroscopic voltage drop, perfectly suited for triggering larger systems. That brutal, snowballing negative resistance is exactly what relaxation oscillators require. But the UJT harbors a severe design flaw. The flaw hides entirely within the math of the intrinsic standoff ratio. Returning to the physical block diagram, we can see why. Eta is derived entirely from the physical location of the p-type alloy on the n-type bar. That means the ratio is permanently fixed at the factory. The engineering consequence is highly restrictive. If a circuit designer needs to alter the triggering voltage threshold for a specific application, they cannot simply adjust the component. They are forced to redesign the entire power supply. The electronics industry realized they needed the exact negative resistance behavior of the UJT, but stripped of its rigid, physical geometric constraints. The modern architectural solution to this rigid threshold problem is the Programmable Unijunction Transistor, or PUT. Though the name suggests a unijunction design, the PUT is classified as a thyristor, operating on a multi-layer junction structure. This schematic outlines the architecture of the PUT, revealing 4 alternating semiconductor layers, P, N, P, N, alongside an anode, a cathode, and a gate terminal. While this internal 4-layer stack operates on entirely different subatomic mechanics, it is explicitly engineered to output the exact same external voltage current curve as the original UJT, but it introduces a critical structural departure. Instead of relying on the internal resistance of a silicon bar, the PUT's triggering threshold is managed by that distinct gate terminal. Replacing the solid silicon bar with a gated 4-layer stack successfully separated the triggering mechanism from the physical volume of the semiconductor. The functional breakthrough of the PUT architecture is that it completely deletes the internal silicon voltage divider from the mathematical equation. This circuit diagram highlights the new approach. Engineers recreate that divider externally, using 2 standard resistors wired to the gate terminal. As the notes show, the PUT fires when the anode voltage rises just 0.7 volts above whatever voltage the engineer programmed at the gate. This architectural shift moved control from the factory to the circuit board, replacing an inflexible physical constant with a ratio the designer can actively manipulate. Externalizing this math unlocks a cascade of operational benefits, beginning with the elimination of the continuous power losses that used to occur across the UJT's internal bulk resistance. As noted in these specifications, the modern performance advantages are clear. The PUT can comfortably operate on heavily constrained power supplies down to 3 volts and reliably trigger with peak currents measured in microamps. By decoupling the device's mathematical function from its physical silicon topology, the PUT enabled the highly precise, efficient, and integrated timing networks